We got a good one. I'm excited about this one. Instrumentation amplifiers. This is what you've been waiting for. So you're getting the keys to the vault today. So my face looks really red, but I think it's I have my, as soon as the sun goes down, my light's a little weird, and I kind of have a big light right behind me, and it's kind of very, very bright. That's the thing about these LED lights. They're just, you get a whole bunch of brightness for not a whole lot of power. So, okay. So we're continuing on looking at different actual practical op-amp topologies. Right now we have a very popular one that's used all over the place, and it's really used when people are trying to do a measurement on a signal that they don't necessarily have control over. So if you've got a signal that you have a lot of, if you have a signal that is a strong signal, it's a voltage signal with a low impedance, it's a current signal with a high impedance. You don't necessarily have to go with the circuit that we're going to talk about at the end of the lecture today, but if you don't have control over that, that's when you want the circuit we're going to talk about. So, but to get started, let's go back to our old friend, the normal difference amplifier. What if we want to have variable gain? So, variable gain is a lot of times a very important tool when dealing with difference amplifiers. A lot of times you have devices where the ability to control the gain is a matter of use, is a matter of device use. So, there's all sorts of things you'll buy that have a little knob, to change the volume, to change the signal strength, to change the intensity. Multimeters have that. Multimeters have, little turn a knob, it'll make a signal get bigger or smaller. And so usually that knob is a variable resistor. That knob's usually a potentiometer. So how would we want, if we wanted to build a difference amplifier with a variable gain, how could we do it? Well, we can't just simply change one of these resistors, right? So one thing could be to change one of those resistors, but if we do that, it's going to be imbalanced. And remember we said we have to keep this network, the two sides, we have to keep this, the ratio of this and this to this and this. That has to be perfectly balanced in a difference amplifier. Otherwise, we get this non-ideal effect. We start to have a lot of the common mode show up. We start to have issues like that. So we want to keep these balanced. We can't just change one resistor, but what we can do is put a variable resistor across here. So we can essentially split this second resistor into two and put a variable resistor in here, sort of create a bridge network. That'll stay nice and balanced, and it gives us a gain expression of this. So yeah, we do have this variable gain here. One downside though is it's nonlinear. So it's a variable gain term. We can use RG to control the overall gain of the amplifier, but it's not the best, right? So if you were changing for instance, if you were changing the scale of a multimeter or something like that, this would not be a good way to, or not the scale of the multimeter, the scale of an oscilloscope. This would, you'd never be able to get down below 1. You'd never be able to get down below this built-in gain of 1. And then also going beyond that, you'd have a sort of a nonlinear behavior. We prefer to have more of a linear behavior. How could we achieve that? By basically just doing this. So one thing we know is that the overall gain of our amplifier is always going to be sort of proportional to, what is it? Proportion. Shoot, I forget that proportional to symbol. Man, how did I get the proportional to symbol? I don't know. I'm just gonna. There we go. That's the. Got to make it up on the fly. So I forget stuff too. It's not just you. Everybody forgets things. Right now, I can't remember the proportional to signal. So it is what it is. But what we know that the closed loop gain of an op-amp circuit is always inversely proportional to 1 over the feedback, right? Basically, we're saying as the more you nuke the feedback of a op-amp, the more the op-amp has to, the bigger an output signal the op-amp has to produce to get the cancellation at its input. So the closed loop gain is always going to be proportional to the inverse of the feedback gain. So what we can do basically is we can just insert a gain stage in the feedback path that gives us an adjustable gain. So we can just insert, in this case, what do we have? In this case, we have an inverting amplifier. We know this inverting amplifier is going to give us a gain of R3 over RG, or proportional to R3 over RG. But because this is a gain in the feedback path, the overall gain of this amplifier is going to be inversely proportional to that. It's going to be scaled by that. So essentially what we're doing is we're giving ourselves a way to nuke the output as it comes back through the feedback path, which means the op amp has to, produce all that extra voltage to adjust for that change in gain. And now we get a much nicer linear behavior, linear variable gain. A couple things to note about this. One, doing adjustable gain this way adds an extra op amp. So we have to add an op amp to get our adjustable gain this way. That can be a fairly high price to pay for linear adjustable gain. Another thing to note is, why is our feedback connected to the positive terminal now? So think about it. Why? So this normally kills an op amp. You can't have feedback to the positive terminal. That's going to result in unstable operation. So why are we doing it here? Because this was an inverting op amp. So what we're doing is we're taking the output and inverting it. And if we are feeding back on the negative of the feedback, we have to feed back to the other terminal. So we have to feed back to the positive. So basically, the bigger this output voltage gets now, the smaller this terminal voltage gets. So in order to correct an imbalance of the input, we actually have to feed it back to the positive terminal now to get proper stable operation. So something to note. We could have used a non-inverting op amp here, and then we would have fed back to the negative input. Why would we not want to use a non-inverting op amp? Because if we use a non-inverting op amp, we're back to this whole kind of a deal again, right? If a non-inverting op amp also is nonlinear gain, so we don't want to, in order to get linear gain, replace it with a nonlinear gain feedback attenuator. So anyway, so this is one way to achieve linear gain, and this kind of works for almost any op amp network. Anytime you just intercept the feedback path and scale it, it's a way to achieve a linear gain control, basically. Being careful to note that if you're using an inverting op amp, inverting topology, you have to feed back to the other terminal of the op amp. You got to flip the op amp. So, okay, that's kind of neat. Cool. Now we're on to the big one, the instrumentation amplifier. So what's wrong with this? This is pretty cool. This circuit here gives us differential input, variable gain, program, we can change the values of R1 and R2 to change the gain of this overall amp. That's pretty neat. We can pretty much do anything. So what's not perfect about this? The biggest thing that's not perfect about this is we have finite input resistance. So the input resistance of this standard difference amplifier is not very high. It's based on the values of R1 and R2, which for normal op amps has got to be in the ballpark of, 50 to 200K at best. So, and you might say, 50K input resistance, that's fairly high. Maybe that's okay. Maybe, but it depends on what our input is. If our input signal is, if we're measuring the voltage across your skin, it's not going to work. Your skin's got, resistance of mega ohms. So if we really want to have an amplifier that works pretty much anywhere, that we can take any signal, no matter how terrible, and amplify it, any differential signal, we really want what's called an instrumentation amplifier. An instrumentation amplifier is considered one of the sort of ideal amplifier topologies. And this is not it. So this is not, I think I chose this graphic so I could refer back to why is this not good enough? But instead I just clicked the back button. So it is what it is. So, all right. So we want to be able to measure differential voltage, have variable gain, and have infinite input impedance. So this is not going to cut it. This has a finite input impedance of R1. And all right. So, well, before we jump to I already showed you. I'm not going to go back and change it. But maybe you weren't fast enough to see that circuit. What would you do if you wanted to take this circuit right here and you wanted to fix this? If you wanted to get infinite input impedance, what would you do? Think about it. Think to yourself. You're an engineer now. You're designing. I'm going to have myself a Lay's Wavy, sponsored by Frito-Lay's. Bet you can't eat just one. All right, snack break is over. What did you decide? How would you change this circuit to achieve infinite input impedance? And maybe you said, I'd add a buffer to the input. I'd take a non-inverting amplifier and use it as a buffer. Just take this, get rid of this right here and just do. Yeah, great thinking. Great thinking. That's basically the idea behind an instrumentation amplifier. But it turns out there's some ways we can sort of take advantage of the structure a little bit better. But if that was what you came up with, is add an input stage, give yourself a Wavy Lay's, sponsored by Frito-Lay. I'm not going to eat another one. That's really annoying. Okay. All right, so let's look at this thing. So one thing you'll notice is, yeah, we have that sweet input stage directly to the positive terminal of the op amp. So, but then what do we got going on here? What on earth is that? It's not necessarily it's not intuitive at all what's going on here. This is just some nonsense that we added here. But taking it as a given, let's analyze this thing. So let's analyze the way this is going to behave. We know that this network, this op amp is going to drive this to V1. This op amp is going to do whatever it needs to do to drive this to V1. And this is going to drive this to V2. But what does that mean? That means that this is V1, and that means this is V2. Well, that's interesting. Now we know the voltage across this resistor RG. So we have some current here. Oh no. Okay, sorry. So we have some current here. We'll call it IG. And we know IG is equal to V1 minus V2. Oh boy. Divided by RG. Cool. But what else do we know? We know that whatever IG is, this also is IG. And this also is IG. How do we know that? Because there can be no current here in the ideal case. There can be no current here. There can be no current here. So we know we have this current IG, which is given by this. And it's flowing through all three of these resistors. So basically, the voltage between here and here, that's going to be IG times 2R3 plus RG. And we got IG is this. So we got this equals V1 minus V2 times 1 plus 2 R3 over RG. Okay, boom, we got it. Okay. So basically this voltage now is the difference between the inputs multiplied by this 1 plus 2 R3 over RG. That's kind of cool because RG now, it's non-linear, but RG is something we can adjust in order to adjust the gain of this stage of the amplifier. But then what do we have? Now we analyze this part. So we analyzed all of this. But now what do we have over here? This is just a difference amplifier. This is just a difference amplifier. So assuming this is an ideal difference amplifier, what's the gain of this stage? The gain of this stage is going to be R2 over R1. And the gain of the initial stage, which we already found, was 1 plus 2R2 over RG. Boy, I hope that shows up. I hope I'm not clipping that bottom of the slide off. So then the overall gain is going to be this gain plus this gain. So the overall, sorry, this gain times this gain. Jeez. So the overall gain is, I'm not going to reinvent the wheel here. I don't know if you can see this over my head. But the overall gain now is going to be oh, what did I say? R2. Sorry, I think yeah. Okay, you got it. All right, now that's pretty cool. So now we have a differential input amplifier that has ideally infinite input resistance, and it has a gain that's given by this. So essentially, the cool thing is we have 2 stages of this amplifier. We have 1 stage gain here and 1 stage gain here, and the one here, a single resistor will change this gain stage. Neat. Now let's see how we can use this. And to see how we can use this for this lecture, all we're going to do is go shopping. So for right now, let's go shopping. If you search on DigiKey and you search for instrumentation amplifiers and you sort by the most popular, you'll find a couple of ones that don't really count by some no-name companies. And then you're going to run across this TI, INA 333. This is a fantastic instrumentation. It's very popular. It's an extremely popular instrumentation amplifier. And look at the circuit for this. This was pulled directly out of the datasheet for this. You can go on to DigiKey right now, look this thing up. This was pulled directly out of that datasheet. And what do we have here? We have a circuit that looks suspiciously like, the circuit we just showed. So this is actually, we are at the point where the stuff we're talking about in the book is actually the stuff that you would buy. So you would actually fork out real money for a circuit that has this circuit inside of it. Now, one thing to note about this INA 333, what's going on here? The gain of the second stage of this is 1. So the gain of the second stage is 1. And what's the gain of the first stage going to be? The gain of the first stage is going to be, looking back, we had 1 plus 2 R3 over RG. So this is going to be 1 plus 100 kilo ohms divided by. Now this is weird. When you buy this amplifier, RG is not included in the package. RG is something you need to connect to this. That is a feature, not a flaw. That is a feature because now you can pick the gain of this amplifier. Let's say we want to gain a 10. We want to gain a 10 for this. We bought this, we ordered it, it cost $3. We want to use it to get a gain of 10, differential gain, basically infinite input resistance. How would we do that? So we want this to equal 10, which means 100 kilo ohms divided by RG equals 9, which means RG what is that? Something weird. $11.1 kilo ohms. So all we need to do to convert this into like a nearly perfect differential amplifier is to hook an 11.1 kilo ohm resistor between those terminals and hook up our inputs and our outputs. What's this reference? We'll talk about this in the next lecture, but basically this is a way to get the output voltage to be relative to sort of any particular reference voltage. So if you, let's say you had, let's say you were amplifying a differential signal that went positive, negative, but you were feeding it into a microcontroller that couldn't possibly have a negative input. Then if your microcontroller was powered by 3 volts, you might feed in 1.5 volts here. And when you do that, now your output is going to be relative to 1.5 volts. Again, well, I'm kind of jumping ahead a little bit right now, but I just want to show you what this pin means if you're actually looking at this data sheet. So some other features: offset voltage 25 microvolts. That's pretty good. So input offset voltage, that's fairly small at 25 microvolts. Input offset current 200 pico amps. What's pico? 10 to the minus 12. That is pretty good. 200 pico amps. You can do better. You can get op amps that do better, but that's for the performance for $3. 200 pico amps input current's pretty good. And CMMR, 100 dB minimum. We talked about why do I say CMMR? I really want to say CMR. CMRR, common mode rejection ratio. Common mode rejection ratio is 100 dB minimum. What would be the cause? Why is this not infinite? Why is this not perfect? Well, the cause is internally these guys. So those resistors, if they are not perfectly balanced, then you're going to start to get a common mode rejection ratio that's a little bit off. Also, if these resistors are not perfectly balanced, that will also have a slight impact on your behavior of this circuit. But so what they're saying though is that's pretty well balanced. We talked last time that for a gain of 100 op amp, which is even better, the CMMR or CMRR to get 100 dB was something like 0.1% accurate resistors. So a big part of designing these types of amplifiers that you would buy from, DigiKey or from Texas Instruments is internally having very accurate balanced resistors. And normally what that means is that they have a way of programming these. Just internally, they usually have ways of compensating for temperature and controlling for process variation. So usually there's some way that they can tweak these things to get them nice and perfectly balanced once you actually buy them. So that's all for today. I'm going to leave it here, introducing the instrumentation amplifier. You're definitely going to use these at some point in time in your career. They're really great. And again, go shopping, right? Check them out. And INA3, I've done designs that use this. I've done amplifier designs that use this exact instrumentation amplifier. I wasn't trying to pick it because I've used it. I literally just sorted by most popular on DigiKey, and this is what I found. But anyway, this is good. This has been really good. We got some wavy lays. We got to talk about instrumentation amplifiers. Let's quit it before I ruin it with some math that doesn't work. I will see you all next time.